So the video today is part 4 on equilibrium. It's part of a multi-part video series on equilibrium. You can find the rest of those videos on my YouTube channel. But what we're going to focus on today is really, as it states up here, that given a K in starting concentrations, can you find the equilibrium concentrations? And within those subcategories, hopefully we're going to learn a few skills, such as know how to set up a reaction table and solve algebraically, know how to set up a reaction table and solve when there's a quadratic formula involved, and also know how to set up an approximation when you're solving an equilibrium problem so that you're not having to use the quadratic formula. So let's get started. Here's a problem that fuel engineers use. So what the situation is that you have a 125 milliliter flask. It's at 900 K. You're basically going to add 0.250 moles of carbon monoxide and 0.250 moles of water, and then let the reaction run with an equilibrium constant of 1.56 at this temperature. What are going to be the final equilibrium concentrations? So prior to this, we've done some pretty straightforward plug and chug reactions, but now we're going to have to come up with a strategy to solve for the equilibrium concentrations. And my recommendations are as follows. Use a balanced chemical equation. That's always critical to doing these correctly. Use this balanced chemical equation to set up a reaction table. Plug in the information basically after you've solved as unknowns. And then you're going to basically plug and chug and solve algebraically. But let me show you these steps in detail. So we're going to work on this problem. So here's what a reaction table would look like. Just basically take your balanced chemical equation, use it to set up columns underneath the table, and basically what we're going to do, if we're writing something underneath carbon monoxide, we're talking about the initial concentration, we're going to talk about how the concentration changes, and then we're going to talk about, here's an expression for its equilibrium concentration. But if the numbers and the variables are underneath carbon monoxide, then that's dealing with that specific species. And by the same token, whatever's under carbon dioxide, under water and hydrogen, and so on and so forth. So let's set up our situation. First off, we were given moles and volume, so we need to turn it to molarity, because remember, equilibrium is set up relative to either concentrations or pressures if it's gaseous. So using that same concept, we can figure out the initial concentrations of everything that's in the reaction. It's always good to go ahead and put up the equilibrium expression, where you put reactants over products. So here we go. We're going to fill in our initial concentrations after they've been converted from moles and volume. So it's a 2 molar carbon monoxide concentration, 2 molar water, and before the reaction starts, so this is the initial concentrations, there's no carbon dioxide or hydrogen present. All right? So the very first thing you need to do is figure out which way this reaction is going to go. So the way to do that is compare Q to C. And in this case, Q is pretty straightforward because the reaction hasn't happened yet. The Q is 0. All right? So it's going to move towards products, and that's critical for the next step. Because what we're going to talk about next is how much change. Well, we don't know the amount of change, so we're going to call it X. And if you think about what's happening, if we're moving towards products, then we know that we're losing whatever the concentration was originally. We're going to lose a little concentration. This is stoichiometrically 1-to-1 with the water, so it'll lose the same amount. 1-to-1 with the carbon dioxide form, so you're going to gain whatever you lose, right? And 1-to-1 here. So the X's could be set up stoichiometrically relative to one of the reactants, for example. So now what you do at equilibrium is you basically express things the way they are in terms of the variable. Well, we started at 2, we changed by X, so the expression for equilibrium is 2 minus X. And this started at 0, it gained X, so the equilibrium expression is X. And now all we do next is we just plug these expressions with the unknowns back into the equilibrium expression. So there's your equilibrium expression. Everywhere we see these equilibrium descriptions with the variables, we just plug them in. And then basically we have one equation equal to 1.56 with one unknown, x. So now what we do is just simply solve for x, apply our algebra. So we collect terms. Basically have x squared over 2 minus x, and that quantity is squared. It's possible just to square root both sides, and you'll get x and 2 minus x fall out equals the square root of 156, which is plus or minus 1.25. And although there might be two mathematical answers that are correct, you know, because this is chemistry, that only the answer that gives a positive value would make sense, since you're taking away a positive value of material. Multiply 2 minus x through 125. Collect your x's, solve for x, and you'll end up with 1.11 molar for x. So anywhere you see an x, you now can substitute in 1.11. And anywhere where you see 2 minus x is going to substitute in, and it'll be 0.89 molar. So now you actually have the equilibrium concentrations. Carbon monoxide, water, they end up at 0.89 molar. Carbon dioxide and hydrogen, they end up at 1.1 molar. And last but not least, you should take these concentration at equilibrium and plug them right back into the equation and double check that indeed CO2 and H2 1.11 squared divided by 0.89 squared, right, equals 1.56. And so you can double check yourself at the end. All right, so let's look at another scenario and see just kind of a variation on the problem. And what's going on here is now not only do we have water or carbon monoxide starting materials in the reaction, we're also going to have some products in the reaction. We're going to throw it all together, and it's still going to adjust to equilibrium. And it's at the same temperature, so the equilibrium constant is still 1.56. So you follow the same procedure. Get a balanced chemical equation, set up a reaction table, plug, and anywhere you don't know how much something changes, assign it an x. So now we're going to start by setting up a balanced chemical equation. We're going to once again use these columns to align our information. The initial information first has to be in molarity. So we take the information we have in moles per liter, turn it into molarity. Go ahead and set up the equilibrium expression. Now let's plug in what we know. The carbon monoxide and water are starting off at 2 molar. CO2 and H2 are starting off at 4 molar. But now here's an important step. Here's where that step comes in, that you compare Q to K. If I solve for the Q here, you're going to actually see that it's 4, which in comparison to the K is actually larger. So actually this reaction is going to run in reverse. It's going to run back towards reactants to get to equilibrium. So that makes a difference in how you plug in the X. So now pay attention. When I plug in the X here, I'm going to lose concentration here and gain concentration on this side, but stoichiometrically it's still related 1-to-1. So at equilibrium, I have an expression for all of these concentrations. I take my equilibrium expression, just plug, right? And now I'm back down to just algebra, where, look, if I take the square root of both sides, then the square will come off this side. Okay? Collect terms. I'm working left to right, top to bottom. Okay? Multiply the 1.25 through 2 plus x, and you're going to end up with this expression equals 4 minus x. Collect my x's to one side, my numbers to the other, and divide through, and x equals 0.67. So everywhere I have an x up here, I now can substitute in 0.67 and get real equilibrium concentrations. So the carbon monoxide, water have 2.67 molar. The carbon dioxide and hydrogen have 3.3 molar. And once again, don't forget to take your answers, plug them back into the equilibrium expression, and make sure that you are doing this correctly. They should equal 1.56, which in this case they do. So on we go. So here's another variation, and the point of this example is just to remind you, you still need to compare Q to K before you decide whether it's a minus x or a plus x that goes into these columns. So here's another example. We're going to work with Phosgene is a reaction where phosgene breaks down, makes carbon monoxide and chlorine gas. The equilibrium constant for that is not real favorable. It's less than 1, right, at 360 degrees. So what we'd like to know is what are the equilibrium concentrations if you start off with 5 moles of monocarbon monooxygen dichloride, or phosgene, and you let it decompose and reach equilibrium in a 10-liter flask at 360 C. So same procedure, set up your reaction table, put the balanced chemical equation above, make sure this is balanced, 1 carbon, 1 oxygen, couple chlorines, okay, that's a balanced chemical equation. Okay, make sure that you're expressing things in concentration, not moles. And it's important to note that really when these reactions take place, they all take place in the same volume, so it's nice because basically everything's divided through by the 10 liters. So as the stoichiometry takes place, you can actually express it in terms of molarity because the volume will be a wash. And that works out nicely. So we know initially that it's all phosgene and that these are 0. So it's pretty straightforward then that if you compare Q to K in this case, Q is going to be 0, so it's going to shift towards products, right? Do the comparison. So now we know that we should be using a minus X from the reactant side and plus X to the product side. Get them down to their equilibrium expression. Plug them back into the original equation. There you go. And now you're going to solve. You distribute the 8.3 times 10 to the minus 4 across the parentheses. And basically what you end up with is a quadratic equation. X squared to the X to the number. Basically, when you see this setup, you know this is a quadratic equation. Is a good way to solve it. Remember that if you have an expression just like this, whatever's with the X squared is the A term. Whatever's with the X is the B term, and whatever is the number standing alone, and that's the C term. That's what these are trying to remind you about. Then you plug it into this quadratic equation and solve, and you'll end up with X. So when I plug these terms into the quadratic equation and solve, I basically end up with X at 0.020 molar. So anywhere I see an X, I can plug that in. Consequently, the half molar minus that 0.020 equals 0.48 molar. And once again, take your final answers, plug them back into your equilibrium expression, make sure they equal 8.3 times 10 to the minus 4. So let me just show you another application here. Sometimes you can shortcut this and not use the quadratic based on the following little approximation. So here's what we did in the prior step. We basically solved for X squared over this. But let me ask you this approximation. If you take away very little, in other words, there's very little change away from the 0.5 molar, wouldn't it be appropriate to use an approximation of just leave that at 0.5? And then your math gets a lot easier. And then you solve and you basically end up with the same answer that we'd gotten earlier, 0.020. But you could imagine that sometimes that might work, but sometimes it doesn't. So kind of where do you draw the line? Okay, and so here's your rule of thumb. If you take the amount of change and divide it by the original amount you're changing away from, okay, in this case we started off at 0.50 molar, but we're changing to 0.02. If you divide these, you'll actually see that it's 0.04. So by not making that change, it only introduces a 4% error. And so using that strategy, and this, once again, this evaluation occurs after the fact. That is, after you've done the approximation, you can figure out what your difference is and see if it makes sense by taking the change in X over the starting concentration. And the rule of thumb is keep it below 5%, and this approximation should hold. Here's another way you can do an approximation. How could you evaluate this before the fact? So think back to what we just looked at. This can be done after you've figured out how much X is, how much the change is. But couldn't you make the same approximation beforehand in some manner? And let's just think this through, that really when you're looking at this reaction, the K determines how much how big x is, right? If k is very large, then the amount of x that changes is a lot, right? So that should influence your approximation. The other factor that you should think about is the size that you're leaving away from. So even though I have a large change in x, if this number is very large, then it's not really going to matter. So really there should be able to be a comparison made between the size of the original concentration and then the size of the k, and somehow combine those numbers in a manner that should tell you whether you can use this approximation. And the nice thing about that is we can do that before we ever do the calculation. So here's how it looks. That basically if you'll take the AO, or in other words the original starting concentration, and you'll divide it by K, then a number that's we've come to find is that if this number that you find in here is larger than 400, then that approximation should stay less than the 5% error mark. And you can imagine there's some play on this depending on the power to which the concentration is raised. It's a good rule of thumb, and it seems to work fairly consistently. That division of original starting concentration divided by the equilibrium constant, if that ends up above 400, you can use this same approximation. And within the precision of the change, that would still be accurate. So if you think about as the AO is rising, then what you're saying is you have a lot larger starting concentration. Or if the K is actually getting smaller and smaller, that means there's less and less change going on, right? It's not shifting to the right, it's probably trying to shift to the left. So in that case, you would still have a good approximation. Another problem, solving for K. So let's do another example and just see what else we can learn. Now, in this case, we're not really actually trying to solve for equilibrium concentrations, right? We actually have equilibrium concentrations. We have enough information to figure out equilibrium concentrations. Can we go back and figure out the K? So the take home here is use the same technique. Set up your reaction table. Set in what you know at the initial conditions. Solve for the final or the change using a variable. And this is also a good example because it points out something about stoichiometry. Look, if this changes by some quantity x, well this, because of its stoichiometric relationship, should change by 2x. So you can learn apply what you learned in stoichiometry to solve this problem. And so at equilibrium, you would describe the new concentration as 0.458 minus x, and this one is 2x. Say, once we have that solved, we can actually just use the information from the reaction table and plug in things we know. And that is the total pressure at equilibrium is 0.757 atmospheres. Well, according to the law of partial pressure, the pressure of carbon dioxide and the pressure of CO together should make this. Then I go back from the reaction table and say, well, I don't know the exact number, but according to the reaction table, I'm expressing the pressure of CO2 as the original concentration minus X, and I'm expressing the pressure of carbon monoxide as 2 times X. Just plug, chug, you can actually solve for X and get that X is really 0.29 atmospheres. And then you can go back into your equilibrium expression and plug in what you know now and solve and see, oh, the equilibrium K in terms of pressure is 2.25. So there's another application, and it also points out the importance of stoichiometry. All right, here's a practice question. And as we so often do, when you see these, stop your video, take a minute, get out your paper and pencil and try and work this problem. When you get a final answer, restart the video and check your work. So let's see how you did. Basically, we're reacting hydrogen and iodine to get this hydroiodic acid. So you, as you know, put in your initial concentrations. Basically, look at your Kc, look at your Q. In this case, Q would be 0 because one of the products is 0. So you know it's pushing towards products, so you know what to do with your X's now. And here's another application where hopefully you've applied the stoichiometry that if this is changing by X and it's in a 1 to 2 relationship, then this will be growing by 2X. So at equilibrium, you can take the original concentration minus x, or you can take 2x as your final answer here for equilibrium. Plug it into the equilibrium expression. And basically, at this point, you can say, hey, wait, maybe we can do the approximation. Maybe we don't have to do minus x, right? So what you do is you take your k, which is 49, and divide it into the original concentration. And in this case, it's very small number, 4.1 e to the minus 5, so you know this approximation won't work. So the amount of change is going to be much larger than proportionally to the original concentration, or large enough that it would be significant if you made that approximation. So we're not going to. We're going to work it on through, collect like terms, get everything to one side equals 0. Now we have a quadratic equation, so we apply the quadratic equation. Okay? Now here's an interesting answer to the quadratic equation. There's two answers that work, but if you'll look, you're talking about what's subtracted away from an original concentration that's already 2e to the minus 3. So it wouldn't be reasonable that you could subtract 4.67 e to the minus 3. So the math doesn't necessarily understand the chemistry because it can work in the negative regime, but that wouldn't make sense in terms of concentration. So I couldn't remove more moles than were present in or more molarity than was present in the original reactants. Okay, so we're going to not use that answer. We're going to work with the 1.7 e to the minus 3, which is reasonable for these. So now we just plug and chug, and you end up with an answer of 1.3 e to the minus 4, or that's 0.13 millimolar, putting it in the original concentration terms. I2 is 2.13 millimolar. And the hydroiodic acid is 3.74 millimolar. And once again, take your final concentrations, plug it into your equilibrium expression, and see if it does indeed equal 49. And you can double check your work. So I hope all that we've gone through today helps you understand equilibrium a little better. And in particular, working on problems where you're given concentrations and you want to solve for the final concentrations. In other words, you're given concentrations at starting conditions, and you want to solve for what the concentrations will be when you reach equilibrium.